Today's topic is going to be on physics-informed data analysis for stochastic power system modeling, risk and stability assessment. A quick summary of the abstract. So I don't want to spoil too much for Dr. Zhao, but there's a lot of changing. Our power system is changing a lot. Right? There's more challenges with intermittent resources. There's a lot of opportunities with, we have a lot of sensors nowadays, a lot of data coming back. So this talk will be about introducing a physics-informed data analysis framework to fully unlock the potentials from data while respecting physical constraints, including physics-informed estimation, inference, learning frameworks for power system modeling, optimization, security assessment in presence of different types of uncertainties, uncertain resources. So, we have Dr. Junbo Zhao join us today. Dr. Junbo Zhao is the Todd M. Cook and Elizabeth Donahoe Cook Associate Professor and Director of DOE Northeast University Cybersecurity Center for Advanced and Resilient Energy Delivery, so CyberCare. He's also a research scientist at the National Renewable Energy Laboratory. He received his PhD from Virginia Tech in 2018, and is currently the officer of multiple IEEE committees and subcommittees. So Dr. Zhao is very active in the IEEE area, won a lot of IEEE Best Paper Awards, and also recipient of the NSF 2025 NSF Career Award, IEEE PES 2024 IEEE PES Technical Committee Distinguished Individual Service Award, and many more. He's also a fellow of IET and the editor-in-chief of International Journal of Electrical Power and Energy Systems. So we're really happy to have you here today, Dr. Zhao. Excited to hear more about this topic. I'll hand back to you for the presentation. Thank you.
Thank you so much for the kind invitation, Wally and Qiushi. This is a great opportunity for us to share what we have been doing for the past few years. So for today's talk, I will share part of the work like my former PhD student, Bendong Tan. He's now assistant professor in Hong Kong Polytech. The topic is physics-informed data analytics, specifically for stochastic power system modeling, risk, and stability assessment. Here is the talk outline. So I categorize the presentation into two major parts. The first one is related to the forward uncertain quantification in power systems. Those are mostly related to static security assessment, as well as the stochastic dynamic security assessment. Then the other part is related to the inverse uncertain quantification problems, where we look at the modeling perspective, particularly on the parameter estimation. So we'll focus more on the dynamic load modeling, particularly the WECC composite model, either for dealing with high dimensional parameters or handling any measurement errors that we are frequently assess and when you are using machine learning approaches. So to begin with, I think everyone is very familiar with the dynamic paradigm changes. Just a basic rule is that for power systems, we always want to keep the power balance between generation and loads. But as you can see, it's very different from the past, where most of the changes are coming from the demand side, right? We're dispatching the generation to meet the demands. Nowadays, we see both hand sides changing. From generation side, we have more intermittent generations, while at the demand side, we have EVs distributed energy resources and some demand response programs. So you will see both generation and demands, they are changing. So it's more challenging to balance them all the time. That means you are trying to see more and more potential risks. For example, voltage limits violation, power flow violation, or transient stability violation, and so on. That's where we want to focus and to develop some approaches to handle that, right? So wind, solar, although under current situation, we may see some slightly decline increase, but from the world perspective, we're still going to see a significant increase from the wind and solar deployment perspective. And as we know, wind, solar, they are stochastic, contain some uncertainties that we need to properly handle. To summarize, actually, here is the problem we're trying to address. So from the input side, again, you see we are caring about power and generation balance, right? So from a power generation perspective, we see there are renewables loads, which they are subject to certain uncertainties. And those uncertainties may be described by probability distributions. And then we have a network of systems. When those uncertainties are regarded as inputs to the systems, then from the output perspective, you are also subject to uncertainties. That's where we are trying to quantify. Either you're looking at the static power flow perspective, and then you may assess probability contingency analysis. If you are interested in transient system stability, that's the stochastic dynamic security assessment. So here, our main goal is really to develop a couple of approaches where it allows us to quantify how those uncertainties are going to affect the quantity of interest. The quantity of interest could be any risks that we're interested in, or any of the parameters we do not have confidence. And that can be fairly treated as two separate problems. The first problem is in terms of uncertainty quantification power system from the forward propagation perspective. This can be explained in a simple example here for the inputs. For example, if you have a certain renewable generation or loads, and you would like to assess how that uncertainty would affect the power system indexes that you are interested in. For example, N-1 power flow contingency analysis, you just treat this as inputs, input it into the power flow model, and you calculate the power flow outputs, and then you assess whether there are any voltage violation probabilities or overloading issues across the system, right? So this is the like forward uncertainty quantifications. The other problem we're looking at that if you are receiving several measurements, and then from the measurements perspective, can you use some of them backward to check whether your model is good or your model is consistent with the measurements, right? So this is a so-called inverse problems given the measurements, observations with noises, and we want to check whether the model is appropriate. If not, can we infer some of the model parameters so that they are consistent? So this is a so-called inverse problems that we're addressing in this talk. So for the forward or even reverse problems, the most commonly used approach is the Monte Carlo based sampling, and this is widely used in uncertainty quantification, right? You sample the probability distribution, and then you forward those samples to the nonlinear regression models or nonlinear models, and then you quantify the probability distributions for the outputs that you are interested in. And then the challenge for Monte Carlo based approaches is that it may be quite computational, extensive, meaning that if you are dealing with some of the operational problems, it cannot be done timely to meet the operational time limits, right? So that's where we think about, can we use an approach to accelerate that process through sort of machine learning approaches? And we categorize this as a surrogate model, meaning that can you use a surrogate model to replace the original power system computational model? Either it's a power flow simulator or it's a dynamic simulation module. By doing that, you can significantly accelerate the process. That's what we are doing. And of course, to build this surrogate model, you have to make sure it is satisfying all the constraints that system must satisfy. And in the meanwhile, it must be representative with quite good accuracy. So for that, we have been doing several applications in power system from the modeling perspective to planning and operation. And in particular for forward uncertainty quantification here, we look at voltage stability. Either it's like a -1 based contingency analysis where you assess the voltage stability, or there might be a -k contingencies where you still are interested in how those uncertainties affecting the system stability. And of course, the challenge here is that how you're going to handle those high dimension inputs as well as topology changes. Sometimes you may have to handle high dimension outputs. For example, you may have many interest variables you want to monitor, right? For machine learning models, certainly there are some challenges if you output a lot of outputs instead of being particular for a couple of outputs. We will show a little bit more details later. From the inverse uncertainty quantification perspective, for example, for the dynamic load model, WAC dynamic load model, it has hundreds of parameters, right? Or some of the inverter-based resources models, it may have more than 100 parameters. Given a certain set of measurements, can you really select and calibrate those parameters out of those 100, right? So that's certainly a challenge, how you are going to deal with the high dimension estimation problems. And of course, how you're going to mitigate the measurement errors or track some of those parameters which are time varying. For example, some of those control parameters you may tune and they may be changing from time to time. And essentially, if you treat them as a black box. And so those are the challenges we want to address. To start with, I want to begin with the probability load margin assessment with n-1 first, and then we extend to n-k based scenarios. So for the voltage stability assessment and the contingency based ones, it's fairly well known. Given certain contingencies, you run the continuation power flow, and that will give you different load margins, and you pick the one with the least margin as a system voltage stability margin, right? So that's what we do, and of course, you can do this fairly good in the past if you don't consider those uncertainties coming from the inputs, and those inputs could be uncertainty from the renewable generations or load changes, right? That's where we want to consider. So if you want to consider those uncertainties, the straightforward way is that you can always sample the probability distributions, get a lot of samples and pass to the contingency-based continuation power flow, and then you run multiple Monte Carlo simulations, and you'll get the stability margin distribution. But again, this will be extremely time-consuming, even for small-scale systems. So here, mathematically, from the load margin calculation, just a recap, we certainly want to maximize the load margin, and the matrix we're looking at is that among all the margins we calculated, what is the minimal across the systems under different contingencies, right? So that's the matrix we're trying to calculate. Now the problem becomes that given wind power or renewable and load probability distributions, how you are going to propagate through those constraints, and at the end you still get a probability distribution over the margins. It's not going to be a deterministic one. Now it's going to be a probabilistic one. That's where it causes some computational challenges. So the first approach we develop here is simple, which we know that continuation power flow is very time consuming. Can we develop more time like computationally efficient approaches where you can really assess the computation power flow efficiently, right? So essentially, you want to develop a surrogate model to replace the CPF module. That's it. So here, and of course, you need to make sure these approaches, it can have the uncertainty quantification like capabilities. And one straightforward approaches that we think about is the so-called Gaussian process, or Gaussian process emulator. This is widely used sort of machine learning models with natural uncertainty quantification. But one really challenge for Gaussian process is that it has like scalability issues, meaning that you cannot handle a large inputs or large outputs. For this particular case, it's fine because we're interested in just one outputs, which is the stability margin, right? While you have to handle the large inputs because there could be large scale systems with hundreds or thousands of uncertain inputs, while the normal Gaussian process cannot handle. So for that, we use the so-called deep kernel emulator, and that deep kernel is really using the deep neural networks to extract further the latent space features and we act the Gaussian process at the latent space to move forward. In such a way, you leverage the power from the deep Gaussian process, the deep neural networks, to extract the key essential features, and then you act the Gaussian process at the latent space. That could make the whole framework work. So to address further with some of the topology changes, a standard way is to use sort of the like transfer learning, and for this case we're addressing n-1, so it will be quite easy because the n-1 contingent or local one topology change will be very easy because it only affects some local features. So you have to really update some local neural network parameters or the Gaussian process model parameters, and then you will be able to handle future new n-1 contingents that you have not seen in the past, or you can quickly adapt your model to assess this scenario. We assessed and find that it only needs like 100 samples or so, and then you will get it updated. It still achieve a quite significant improvement over the computational efficiency. So here's the results, which just show a very simple systems, while in the original paper we showed before, it has a larger scale, over 1,000 bias systems. But the case we want to show here is that if you use Monte Carlo as a benchmark, the red curve is a benchmark, and if you use the transfer, like deep kernel emulator, and you'll do a pretty good job for following the Monte Carlo baselines. While the other way you can do is that when there's expected topologies, you can always retrain your model, right? With new data and everything will be more time consuming, but we find that even with retraining, you are not achieving the similar performance as compared to transfer learning. And of course, if you don't do any transfer learning, you are going to achieve bad results because your model does not have the scalability or adaptivity to address some of the topology changes there. So this is really a key conclusion we want to show. And of course, from the computation perspective, this can be done within a couple of seconds, within a second also, while for Monte Carlo, it may be a couple of hours to get it done. So we make sure that from the accuracy perspective, it met similar performance as Monte Carlo while being much more computational efficient. So this is the first example we want to show for simple topology changes. Now, the other really challenging problem is that when you have a massive topology changes, right? For example, for those rare events going above n-2 or n-3, how you are going to handle, right? So again, here, this is a recap. Like you may have multiple, events, and we categorize them into the n-k events. And of course, you can consider this through the Monte Carlo-based sampling approaches. You can calculate and you get the results. But the challenge in here, you may need to have over 100K samples so that you can really capture some of the tail events. The tail is really something of interest, and the tail will tell you, will indicate how much or what is the probability of getting some violations. And of course, to getting the risk distribution is a little bit challenging. That's why even more massive like simulation or samples is needed, right? And of course, to handle this type of rare events, we have to develop a more efficient approaches. What we did here is that we did follow the similar approaches we developed in the previous slides. We first used the deep DNN to extract the latent features, and from the latent space perspective, we use the so-called variational sparse techniques so that we can really extract the key elements. And of course, for those key elements, we use sort of the k-means based clustering so that we can really identify some of those risk errors. They share some common features because the system is sparse. Some of the features may share some common commonalities. So we want to cluster it and making sure that our latent space can do a good job for representing some different common features while extracting the key n-k contingency phenomena. And with that, with the newly attractive features, we input to the variational Gaussian process, and variational Gaussian process is even more powerful as compared to the Gaussian process itself, because it can handle a little bit larger input space. So by doing that, we find that it does a much better job as compared to the previous approaches, which will show comparison results. And of course, here we certainly use a so-called SVM, support vector machines, first of all, to determine whether we should for the new contingencies or new samples under the trained surrogate model, or those of the M-K scenarios we have never even seen before. You have to run a power flow solver. So this is something we do our so-called hybrid model. For most of the cases, you still go through the surrogate model, while for some cases like -5, 6, there's no possibility that you can train that into your surrogate model. We just use power flow, because those are very, very few cases. If you only run power flow, it can be done very quickly. That's what we did here. So you'll see for the framework perspective, we first extract the probability distributions and we model the correlations. We are the copula-based statistics. So most of the cases, like 90% of these contingencies, we just get a surrogate model that we mentioned before, either through the resampling-based assessment or the SVM to judge at the beginning, right? To make sure that it follows for which category of contingencies, and then you use that approaches through the surrogate model to do the risk assessment. While for some of those contingencies, it goes beyond the normal, like contingency we consider. If it happens in reality, you just pass through the power flow solver. And then you will still get the probability distribution on that. So by doing this, it allows you to consider more complicated scenarios. So we tested on this modified European 1,345 bus systems with 21 farms and some of the uncertain loads. And from the computing perspective, for the proposed methods, it only requires 1.7 hours to perform the assessment. While if you use Monte Carlo and our hyper, or enhanced Monte Carlo approaches, still consumes a lot of, like hours to do it. Remember here, the total hours here we do here is we consider all the possible scenarios. That's quite massive. While for the typical ISO systems, you may have a credible contingency list, and if you provide that, it will be significantly reduce the computing power, that we require to do it. Essentially here, we generate over 1 million n-1 to n-9 events. So that's a massive data set. But even with such a massive data set, we managed to really do a pretty good job for categorizing the tail events. For example, if you compare the proposed methods with the Monte Carlo-based samples, they fit quite well with the tail events. For the HMS, I think this is a Harding, I think a Lardy hybrid cubic or enhanced Monte Carlo approaches. Due to those, sampling approaches, it was adopted. For the tail events, it may not be really good at capturing those. So it has certainly some errors in the tail characterization as compared to the machine learning-based approaches we developed here. So the other problem we are looking at, for the previous two, they are related to the static assessment, right? It's power flow based. But now let's look at the more even challenging problems. Is that when you are subject to the contingencies or a fault, three-phase short circuits, and then whether the system is going to be stable or not, right? So the problem is that after the fault is cleared, are you able to right away predict within milliseconds the trajectory of the system dynamic changes, right? If you can do it, then you still have a couple of seconds probably to do an emergency control. That's where we are having in our mind. So the purpose here is that can you develop a so-called surrogate model to reproduce or replace the time domain transient system stability assessment modules, which will be very time consuming, And with the PMU measurements where any of the initial conditions supplied by the dynamic state estimator or linear state estimator, and then you use that as input data to your surrogate model, then you can immediately output the predicted curves, the oscillatory curves, and that will tell you whether the system is stable or not, right? That's something we're going to do. So we extended the previous surrogate model we developed. If you remember, stochastic variational deep kernel regression we developed before, but we extended it to be multi-output and multi-input scenarios. And of course, we input the topology. As you can see from G here, those are the graph of the physical networks, because we do want to consider some of the topology variations naturally instead of training and getting everything as an input, while we also expand to deal with the multi-outputs. If you remember for the previous case, what is stability will be single outputs, right? That's the stability margin. But here, it's much more challenging because you have to output large dimension space in terms of the dynamic state variables. For example, here, the X is dynamic state variables. It could be rotor angle or rotor speed that you are using for transient system stability assessment. So from the output perspective, that's even more challenging. You have to handle a large dimension outputs. So that's where we developed the so-called multi-output surrogate model. It allows you to deal with large dimension inputs as well as the large dimension outputs. So that's more details, of course, you can find in this paper. It has a lot of mathematical derivations and so on. But the key role here is that, of course, the unstable and stable scenarios, their curves can be quite different, right? So we would like to, first of all, develop a out-of-step generator detector so that we can clarify whether the current samples, they belong to potentially unstable scenarios or stable scenarios, so that we can build two surrogate models. One is to predict the oscillatory process. The other way is to predict how the system is likely to lose stability in terms of the curves, so that they can still give you a little bit of time to act on the emergency control. That's where we're trying to achieve. So from the training perspective, you are going to generate massive data in terms of the dynamic trajectory database, and you'll consider both the stable and unstable scenarios, right? And when that is done, and then use the real-time PMU measurements or PMU-derived dynamic state variables, so dynamic state estimator, and then you input into the ensemble predicting methods, and then we will get the post-fault trajectory predictions. I will show one result here for the 145 bus power systems. So you see on the left-hand side, this is the stable scenarios. And of course, remember, for our developed approaches, we always have the so-called uncertainty quantification associated with that, which is a confidence interval. So for our stable scenarios, we pick a couple of rotor angles, like ground truth ones, prediction of rotor angle, here with uncertainty quantification, and rotor speed. We also show the uncertainty quantification. It does pretty good job if you compare the curves. It's quite similar, and everything sounds well. While on the other hand, you see for the unstable scenarios, we can still do a pretty good job for predicting. And of course, one very interesting scenario, you will see that the uncertainty quantification range is going to be really big, to be bigger and bigger. That could be another signal indicating the prediction is going to subject to a lot of uncertainty. It's not really trustful up into a certain large uncertainty quantification interval. And the other thing I want to point out that you see our prediction starts right after the fault is cleared. I think this is very important because you will have a limited time to predict the curve, oscillatory behaviors, and act as emergency control to correct and make sure the system is stable. I mentioned 3 applications in the forward uncertification, and then we would also be very interested in inverse uncertification in power systems. One particular interesting example is on the dynamic load modeling, and we picked the WAC WCC composite model as the example. You'll see it has multiple type of motors with electronic loads, DERs, different types, and static load. And if you count on the parameters, it is over 100 parameters. So it's really challenging if you are given just a couple of set of measurements, how you are going to determine which parameters they can be identifiable, and how you are going to infer those parameters with the limited set of data. Okay? And of course, for the model itself, it has strong nonlinearity, and of course, the high dimension parameters we're trying to address, right? So from the mathematical model perspective, you can treat this dynamic load model as the function f, right? This is the function f, and y is the measurements that you are measuring from the terminal of those dynamic loads, right? It could be PMU measurements from real reactive power, voltage, magnitude, and frequency that you are measuring. So from the replay model perspective, you can treat the voltage and frequency as the input to the f theta, and then you will use the original model f theta to output the real and reactive power. And that's where you are going to compare the measured real and reactive power with the model outputs. If there's a significant differences, you'll see our model is not good. I have to calibrate our model. That's where it triggers the parameter inferences out of that. And of course, there could be a question, since there are over 100 parameters, which set of the parameters they are in charge of those discrepancy, right? So you have to do a sensitivity analysis to identify that. But this sensitivity is not like the traditional one we have done, like linearization or trajectory-based sensitivity. We want to have a global overview of which parameter is contributing to which percentage of that discrepancy, model discrepancy. And we use the sparse polynomial chaos expansion approaches. At each time instant, we build the so-called sparse PCE models, and that allows you to assess at that time instances what are the parameters contributing to the model discrepancies. And by doing that, you can select upon from which time to which time window, what a set of parameters they are more responsive. While from which time window to another time window, what are the other parameters who are more responsive to the discrepancy. So in that way, you can have multiple stages of calibration based on the active participation of those parameters. That give you really the power to handle the large dimension. And of course, here from the proposed method perspective, we use the conditional mask autoaggressive flow so that instead of just getting the values, inferring those values of the parameters, we also automatically have a probability distribution associated with that. I think that's something we're interested in, because it is not going to be just one parameter. We want to know the intervals for that parameter changes and uncertainties associated with that parameter estimation as well. So I want to show here for this example, if you look at the two values here, the two values, and this is the distribution for different approaches, right? Here the CAVE, this is the approach we developed in collaboration with another colleagues for conditional variational code, CAVE. If you remember, CMAF is the approaches we developed. As you can see here, by doing this type of procedures, we mentioned that it does a pretty good job for getting very sharp, like very narrow probability distribution to cover the two values of the parameter we're interested in. So if you don't adopt the approaches we developed, it has a large discrepancy, because if you look at the mean, it's still far away from, if you look at the x-axis, it is far away, and probability distribution does not necessarily cover the two values that we are pointing out here, right? You see the different red dots where the two parameters are located, and those red distribution covers well with a narrow probability distribution, or histogram showing covering the two values. So I mean that we did a pretty good job for covering that. And we also tested multiple different distributions of the parameters. We also tested different deviations from the true values and so on. So for more details, feel free to look at the papers we mentioned before. I think here later I'll show. I think probably here. This is the paper you can check where you'll see multiple testing scenarios, the mathematical derivation behind. And of course, for this work, we really didn't consider the measurement error. And of course, we know for PMU measurements, it is always subject to measurement noise, right? Sometimes it may be noisy, and sometimes it may be good, and so on. But anyway, we really need to consider the noises, the measurement noises. I don't think really for many of those existing machine learning approaches developed, they are spatially tailored to handle the measurement noise, right? And we did find that the measurement noise is affecting the estimation performances. Sometimes it may cause divergences. So to deal with that, we want to develop a surrogate model to accelerate the inferences. And on the other hand, instead of using the Monte Carlo based approaches to infer the parameters, or the traditional Bayesian-based approaches, we developed a derivative-based Monte Carlo sampling approaches that allows to do a better sampling of the parameter space and help us identify the right set of parameters that can yield the right set of parameters that of interest to us. So here, this is the main concepts related to the Hamiltonian Monte Carlo approaches. It has different like different steps, including constructions, like forward load models, the prior distribution. You have to assume, a prior distribution associated with the parameters. And then you have to do the updating of the parameters. You have to decide the step size, and then you accept whether the parameters you identified, they are a good set, and then you update based on the old estimation results. So this is the main, like steps behind the HM methods. And here shows the more, overall framework of the developed approaches. First of all, we developed surrogate models. We conduct the sparse Gaussian, sparse polynomial expansion-based approaches to identify and rank the sensitivity across different measurement sets, right? And this is the global contribution of the parameter set. And then from the step 2, we use those generated samples to train a surrogate model. And from here, we do the posterior distribution estimation according to the HM, Hamiltonian Monte Carlo approaches to infer further the parameters associated with the model, and also the probability distribution associated with that. And here the estimation is more like a sampled parameter, because this is the posterior inferences. So we will use the sampled, mean of the sampled parameters as the final estimation. Of course, since you have multiple samples, you can have a probability distribution associated with that. So we tested under actual scenario. So this is the actual responses, actual disturbances captured by the micro PMUs, and you see a nice phenomenon for the fault, induced slow recovery phenomena. Right? After the fault, it takes a rather long time to recover due to the motor actions, and this is the actual voltage curves, and we also use the voltage active curves as well as the frequency as the input to the surrogate model. And remember, since those are field PMU measurements, it's subject to the noise, right? So we, with the noise as inputs, active power and reactive power as the outputs, you verify whether the calibrated model is good. And then you will see it here after calibration. Approaches, does a pretty good job for matching the actual, responses. Of course, you see the actual responses can be quite complicated because the WAC model is not 100% true to approximate reality, but it captures quite good the major trends. And for before calibration, actually, we did quite extensive parameter tuning. And that's why you see it looks like
before calibration is does not bad because we have already done a lot of tuning, before the calibration. And if you do find another event, it will show you a large discrepancy between before calibration and after calibration. We also tested on some of the synthetic data sets, and we will show significant differences, which you can find in the paper here. I think later I will show in the references. You'll find the more details on the paper in the reference list. Lastly, if you do our estimation under synthetic parameters, because under such scenario, you know the true value, right? Well, for the previous case here, since this is a field measurements, you don't know the true value, right? You can only compare after and before and after calibration. The similar conclusion, after even you are subject to noises, different levels, different deviation of the true values, we can still capture quite well with the developed methods in terms of the parameters. And this shows nicely the histograms, and it shows the rate curves capturing the true value, right? The dash, vertical lines. This is the true value of the parameter set. So in conclusion, we show that really the surrogate model can help you significantly reduce the computation burden in terms of the security analysis, either the contingency analysis or stochastic dynamic security assessment. On the other hand, by using the surrogate model together, you can do a pretty good inferences of the parameters, and that can help you improve the Parsons model and also assess the Parsons operation. And we are working, doing a more difficult job in terms of the time Orion, composite load modeling. This is even more challenging because you have to identify the time Orion visibility or identifiability of those parameters, and then you need to act on and calibrate from time to time. This is more challenging. And also for the probabilistic conditions analysis, we haven't done really a system with over 10,000 bus systems. That requires another scalability, right? So we're currently working on further enhance the scalability to handle a large scale systems. That's where, for example, at the similar size of the ISO systems. For example, we do have like some of the system size as ISO in England. We would like to see how that can work for the 20K plus, large systems, and whether some of the machine learning approaches could still be working for carrying out different tasks. I did want to show that for the 20K, ISO New England systems, we use the actual data systems to test the machine learning based approaches, and it worked quite well. And that paper is currently under revision under Nature Communications. We can share a little bit more results later once it is accepted for publication. So we are very happy that at least for the static part for large scale systems, it is working. The next step is to extend and see whether we can handle dynamic systems with over 20K buses with massive renewables and synchronous generators. And of course, will be very challenging to see, but very exciting to explore further. So here are some of the representative papers or references we had, and those results are based on those publications where you can access. With that, I will conclude my today's talk, and then I will be very happy to answer any questions you guys may have. Thank you.
Thank you, Dr. Zhao. That was a really great talk, and thanks for also walking through what the next your future directions are. Looking forward to reading that paper that you mentioned too. We're open for a Q&A session now. Please feel free to kind of come off mute and ask your question directly to Dr. Zhao. Or you could also drop it in the chat and I can ask it on your behalf. So Dr. Zhao, while we wait for questions, I think there's one question in the chat.
Mhm.
It was from your post-fault dynamic trajectory prediction section. So this is a question from Sungjo. My understanding is that the proposed method is able to predict the entire trajectory in one shot, given initial measurements, 2 time steps. What feature of the framework allows this one-shot prediction that bypasses the commonly used rolling prediction framework?
So here you see I want to emphasize the motivation why we are doing one-shot based prediction. And our application is really focusing on emergency control. Emergency control means that you do not have much time to act. You have to do it right away, right? Because the system can be unstable within 1 second or less than 1 second. So you have to, after the fault is clear, for example, after the fault is clear, can you use PM measurement at that exactly at that time instances, input to your model, and then with milliseconds, then you come up with a curve for the next 2-3 seconds or 5 seconds. You see, okay, this is a curve I predicted, and show that you are going to have stability issues. So you have to act right away instead of rolling hurry down. For rolling hurry down, you do not have time to act. So here, really, we are focusing on the emergency control. With the time is really, really limited. You have to act very quickly on that.
Gotcha. Thank you, Dr. Zhao. Singja, please feel free to come off mute if you have any follow-up or you're satisfied with the answer. I'll move to the next question. This is from Syed. For load modeling work that you are doing, are you also accounting for the temperature or the embedded climate models in any way?
So do you mean like whether we consider any climate, models
Yeah.
for?
Weather information, weather data.
No, not really, because this is a dynamic node model. It's not like a static model we are considering. You have to consider the weather parameter or weather condition changes here, right? But I think there could be one thing of interest is that due to the weather changes, and it could be relevant to the real time or time horizon calibration of the WAC models, right? Because you see, you do have DER included in the model, and if the weather changes, some of those DERs may be affected, like portion, like percentage, right? Because for each model here, you have certain percentage associated with that. So I would say probably in the the percentage associated with that DERA will be affected. So that is part of the time horizon identification that we can do. But normally for a WAC model, it depends a lot on the disturbances, and it does not emphasize on any climate impacts there yet.
Gotcha. That makes sense. So this one is from SD. So why have you named this model as surrogate? Specific term called surrogate.
Yeah. So surrogate means that you want to find a model that can do similar job as your original model, right? Either it's a power flow model or DAE-based simulator. And surrogate means that I can replace you. But of course, I need to sacrifice certain things like accuracy level. I cannot 100% accurate as yours, but I achieve big benefits being much more computational efficient. That's why we see surrogate model. We want to have a like a model that can do similar thing as your original model. This is a so-called meaning of surrogate, right?
Absolutely. So we kind of, we want similar features, but similar outcomes from the model, but it has other efficiencies that we
Yes.
call, like you talked about latency aspects.
Exactly.
This one is from Sharath, and I think so how to model loads when truncated at sub-transmission system. So I think its question is around, we're going to see only the net load. I'm guessing, if I understand the question right, it's it's that black box of that load. Like, how do we kind of disaggregate that renewables and the load behind that subtransmission and account for it in the analysis?
Yeah, that's exactly in the WAC dynamic load model is doing, right? So originally this is structure. You see, okay, I know my distribution systems are going to have different type of motors and different type of electronic load, static load, and DERs, right? I know they are going to be there, but I don't know the parameters associated with them. Either the percentage, what is the percentage for motor A, motor B, motor C, motor D? I don't know, right? So, but I know this is a mathematical model you have to follow. And then based on the past experiences, like the power system planners, they have initial, parameter data sets. Like if you ask ISO New England or if you ask PGMs, they will let you know that I did some surveys before, and this is likely the percentage that you are going to get for a certain range. Of course, it's not going to be a single parameter. It will be likely in that range. So now the problem is that how you are going to identify a proper set of parameters that satisfy that ranges put for each of the components, right? And that's the task we are trying to do. It's not like totally, no knowledge about the percentage or components of that. It's not really like a totally black box model per se.
Gotcha. That makes sense. I don't see any more questions on the chat, but one last call for any questions from the audience. Again, you could feel free to unmute and also ask your question directly to Dr. Zhao. Yeah, no, I got a couple of comments saying, people missed the earlier part, or, will this be recorded? Yes, this talk was recorded. It will be available on our website. I'll drop the link to our website where we host all the materials. So we'll get information from Dr. Zhao uploaded, as well as the video. So you could always go back and refer this talk. But since we don't have any more questions, I wanted to take the time to thank Dr. Zhao today. This was a great talk. Thanks for taking time to share your work with us. Hopefully, we'll look forward to that paper that you mentioned, and maybe have you back again to share your work in the future. But thank you so much. And I wanted to thank all the audience who were able to join the talk today too.